Imagine you have collected years of rainfall and streamflow data from a catchment. One of the first questions you might ask is, which rainfall station has the greatest impact on the stream flow? Or perhaps, how long does it take for rainfall to influence runoff? Or even, how many rainfall antecedents should I include in my machine learning model? Fortunately, there is one statistical tool that can help answer all of these questions. It is called correlation analysis. In this video, we will learn about correlation analysis, how cross-correlation and autocorrelation work, and most importantly, how they are applied in rainfall runoff modeling. Let's get started. This topic is presented in two episodes. In the first one, we covered the theory, strength, and limitations of correlation analysis, while the second episode focuses on applications in rainfall runoff modeling along with a few numerical examples. Correlation analysis is one of the most widely used statistical techniques for analyzing hydrological time series. Its purpose is to measure the degree of association between two variables. In hydrology, these variables might be rainfall and runoff, rainfall and river water level, stream flow at two gauging stations, or even a hydrological variable with a lagged copy of itself. The most commonly used measure is the Pearson correlation coefficient, usually denoted by R, and can be calculated like this. The correlation coefficient ranges between -1 and 1. A value close to 1 indicates a strong positive linear relationship. On the other hand, a value close to -1 indicates a strong negative linear relationship. Of course, values near 0 indicates little or no linear relationship. The following table provides common qualitative bands as a rough guide. These categories are only indicative, and the interpretation always depends on the specific hydrological application. Before using Pearson correlation, remember that it assumes a predominantly linear relationship and is sensitive to outliers. It also performs best when the data are approximately normally distributed. The cross-correlation function, or CCF, simply calculates the Pearson correlation coefficient repeatedly while shifting one time series relative to the other. For example, the CCF between runoff and shifting rainfall data. By calculating the correlation over many time lags, we obtain a cross-correlogram. The lag corresponding to the maximum correlation often represents the characteristic response time of the catchment. Also remember that the strong serial correlation or autocorrelation within rainfall and runoff records can sometimes create misleading cross-correlation peaks. In advanced time series analysis, a technique known as pre-whitening is often applied to reduce this effect before computing the CCF. In autocorrelation function, or ACF, instead of comparing two different variables, we compare a variable with its lagged versions. The resulting ACF describes how much memory the hydrological system possesses. The ACF therefore provides valuable information about persistence within hydrological time series. Like any statistical technique, correlation analysis has both strengths and limitations. Let's know more about them. Its major strengths include simple to compute and interpret, computationally efficient even for large datasets, excellent for exploratory data analysis, useful for estimating response times, and valuable for feature selection in rainfall runoff modeling. However, correlation analysis has several limitations as follows. First, Pearson correlation measures only linear relationships, so strong nonlinear relationships may not be captured. Second, it is also sensitive to outliers, meaning that the extreme flood events can distort the results. Third, hydrological time series often exhibit non-stationarity, seasonality, skewed distribution, and many zero values, particularly in rainfall records. If these characteristics are not properly addressed, they can produce misleading correlation estimates. Finally, remember that correlation does not imply causation. A high correlation between two variables doesn't necessarily mean that one causes the other. In hydrology, correlation analysis serves as an essential exploratory tool for understanding the relationships hidden within time series data. However, like all statistical methods, it should never be used in isolation. Always combine correlation analysis with sound hydrological reasoning, data visualization, and physical knowledge of the catchment. When used appropriately, correlation analysis becomes one of the most valuable tools for any hydrologist. If you found this tutorial helpful, please don't forget to like it and subscribe to the channel for more videos like this. Thank you for watching. I will see you in the next one.